Okay, so now we're going to go into the next area of the portfolio, the Smart Innovation Portfolio, and we will talk about realization. We have Aaron Frankel. Aaron and Mike will give you a demonstration of our realization. Okay.
Thanks, Paul. Can we cue up my slides, please? Oh, boy. So our next demonstration is about manufacturing. More specifically, it's about discovering new and better ways to make products. So we've set out to answer this question. How can digitalization of manufacturing processes help to improve your business? And we'd like to show you how in the context of a real customer case study. See, our idea was to build a digital twin of the production system and use that digital twin to challenge conventional approaches to design, manufacturing, planning, and production. But before I tell you what happened, let me explain how we set it up. So we selected to work with a company that has a rich history in manufacturing. And we gained access to the production facilities, the data sets, the design and manufacturing departments for a high-tech electronics component, this industrial nanobox PC. Siemens was in the process of developing its next generation nanobox. And we learned that the nanobox manufacturing process is not unlike many other companies. There are silos of information, there are disconnected systems, and even some paper-based processes. So using our PLM tools, we created a complete digital twin of the process and the production system. And we digitalized that process all the way from product design through to manufacturing execution, and we connected all the steps in between. So for today, we selected to share with you what we learned in these 6 areas. Can we cue up the live demo? So we start our demonstration in product design, and we can use the digital twin very early in the design process to help us identify the root causes of manufacturing issues that can affect the build, quality, and the warranty of parts. So with a digital twin, we don't have to wait for physical parts in order to do tryout builds and inspect assemblies. We can use the PMI on the model and a basic description of the manufacturing process to help us digitally produce thousands of virtual products and then look at how tolerance stack-up affects the overall quality. So here we're going to simulate 1,500 digital builds of this nanobox. And almost instantaneously, we can see that 9.5% of those builds are going to be out of spec. And this happens to be caused because of those 2 panel screws interfering with the digital connector. And we can also look a little bit further and see that the top contributor to this interference happens to be the float of the PCB board. So we've got a couple options. We can look at evaluating a design change, for example, and we can change the nominal hole size of the standoff that holds that PCB into place. And in this case, we're going to tighten that nominal hole size, and then we can rerun our analyses, and we can see that we've managed to eliminate that variation. So this is just one example of where the digital twin can help us remove the total cost of poor quality and potentially eliminate a warranty issue. Give me the slides, please. We often hear how product design and production get out of sync, which can lead to costly late changes and even production delays. This is because many companies tend to use spreadsheets to make their manufacturing plans, and other companies tend to use their ERP system. But both of these tools lack that live digitalized connection to the product bill of materials and design information. And so in this next vignette, we'd like to show you a better way on how you can define a manufacturing plan. The manufacturing plan ensures that the production process is going to work properly once you get into manufacturing. It can help you minimize waste. It'll help you ensure that the right tools and resources are available at the proper stations when production is ready to start, and ensure that you can hit your performance targets. And so to achieve this, you always need to be engaged with your live product data. And you need to work in a highly visual and interactive environment that gives you a clear understanding of what your production process is going to look like. You basically need a digital twin of your production process. Here we've navigated to our Mexico plant where we're going to manufacture these nanoboxes. And we've received a bill of materials update from the design department. And our task is to create a new manufacturing operation to assemble the nanobox cover with the provided fasteners. So we can use Active Workspace to plan out our manufacturing plan. We can define our manufacturing bill of materials. We can create a process, an operation, and we can assign that operation to the different operators that need to perform it. And then we can go into the details and specify the specifics about that task. We can specify with a basic description of what that person's supposed to do, an image, and the time it takes to perform that particular operation. The time's very important because it gives us that bigger understanding of whether or not we're going to be able to hit our performance targets. And there's different tools that we can use to input time. We can use SAM tables, for example. We can also use company standards based on clock time that somebody's performed in the production environment. And once we have all of our different times specified for the operations, we can roll them up and do a line balancing study. And when we look at the line balancing study, ultimately we're trying to make sure that we're achieving that target takt time, that target production performance of being able to output a number of components based on demand. We can see that we've assigned too many operations to the same station, and we can easily move these different operations forward and backward into the process. Those tasks are sequence intelligent, so they understand their dependencies. Won't allow us to move something if we have to finish something before we get to that particular task. And once we complete our study and we know that we're going to achieve our target performance, we can generate reports and ultimately use these reports as a basis for our electronic work instructions when it comes time to release this particular process into the production environment. Here we're using our standard Team Center workflow process to release this for review and sign off from others in the organization. Next, we're going to look at the manufacturing layout. And for many manufacturing layouts that are done today, AutoCAD and FactoryCAD are useful and simple tools, but for next generation manufacturing, we're going to have to design our manufacturing layouts a bit differently. So next generation manufacturing is going to be more flexible, more automated. The production line is going to last for decades and not years, and it's going to need to be adaptable to personalized products, as well as new processes and materials that we haven't thought of yet. This means it's going to be important for design and engineering of the production system to be complete with that mechanical definition, electrical, and automation capabilities, and be able to keep it linked with the entire product definition, as well as all the other systems that are in the manufacturing ecosystem. And so here we're designing the nanobox layout, and this particular layout is going to be in our Mexico site. We're using our line designer application to simply drag and place the different parameterized components into the layout. We can adjust the different dimensions to the standard sizes, for example. And what's not immediately obvious here is that this entire layout is being managed by Team Center. And this means that we have that direct access to the definition of the product and the up-to-date definition of the product so that we know exactly what kind of tools and resources we need to have in this particular station. Once we finish the manufacturing layout, we can then produce those typical plan views that the facilities department is going to need in order to be able to begin the actual installation of the equipment in the production environment. And additionally, because we've done this with Team Center, we have access to a richer set of information about the different components in this layout. For example, we can see what suppliers are involved with our production line. We can also see which particular pieces of equipment might be long lead. All of this is going to help us prepare and better plan so that we can hit our start of production date. And when the digital twin of the process is defined correctly, we know that the real production process is going to run well. And for our NanoBox case study, we digitally defined all of the assembly details in the context of our production layout. So nearly all assembly processes depend on people, and we have to be very careful to consider the human performance aspects of assembling products as well as maintaining our equipment in production, and ensure that the intended worker population is going to be able to complete their tasks. We need to make sure that these workers are able to reach their tools properly, reach the product, as well as see what they're working on. And simulation models have become much more intelligent. They're able to allow us to do quantitative analytics on human factors and ergonomics related to the assembly process. Here we're assessing the working posture of Jill while she's putting together the NanoBox. And when she turns yellow, she's exerting herself just a bit too much. And over time, this could cause some injury or potential fatigue. See how she's leaning over the station a little bit too far to put the bolts in? This is just giving us an indication that we need to be aware there's a risk here. And we can look at the simulation of the complete process and roll it up into a nice report that we can use to help us optimize and make sure that we build out these different areas of fatigue and keep it for documentation. We can also use these simulation models in our electronic work instructions to help our operators comprehend a little bit more thoroughly what we expect them to do when they get into the production environment. Can we queue up the live demo, please? I also need my assistance, thank you. Ready? So all around the globe, we're experiencing an increased use of automation. And what's really fascinating here is that we're seeing the robot coming out from behind the cage and working next to people. And so in our particular case study, Siemens wanted to evaluate different upgrades to manufacturing flexibility and their effectiveness. We wanted to explore a more semi-automated process where we had robots and humans interacting together. And so we were able to do this very inexpensively by doing it in a digital environment. And we're able to do a little study here to see if this dual-arm robot was able to complete its operations in the context of that layout that we just designed. And we can see here that we've got an interference between the robot arm and that conveyor. And so we've gone in and we've updated our manufacturing layout. And now we have the ability to, again, check to see if this particular robot can complete its operations in the context of the adjusted layout. We moved the conveyors out a little bit. We reversed the assembly table. And we can see here that the robot is able to completely fulfill the defined tasks. Now, we can also just as easily swap Jill or Jack back in for where this robot is standing to see if this human operator can perform their tasks in the context of this layout. And when the digital twin of the process and the production system are defined correctly, the production will run well. But what happens when the production process isn't running so well? What do we do then? Live demo, please. So the power of the digital twin doesn't have to be just applied to individual processes. We can apply it in the context of the complete production system. And when the production system isn't running to its expected throughput, without simulation tools, it can be very difficult to visualize where the different problems might lie. It can also be very difficult to visualize what a new process might look like and be able to evaluate different options to see if those are going to be able to satisfy the performance requirements. So in our NanoBox case study, we set out to validate our system and optimize its throughput, and we were looking at two different studies. We wanted to see if our robot operator interaction was going to be able to satisfy the target throughput for the process. And we wanted to confirm that the material was able to flow freely, properly through the entire plant. So we studied two different operator robot cases. The first was to have the operator actually follow the NanoBox through the assembly station, through each of the different steps, and even stand next to the robot and wait for the robot to finish their job. And this simulation is showing us in this graph with the gray portion of that bar that the operator ends up waiting almost half the time while the robot is doing its job. So that's not a very efficient process. We can study another approach, and the other idea was to have the operator pick the NanoBox that needs to be assembled, go over and place it next to the robot, and instead of waiting, go off and do something else. Take a finished NanoBox from the robot and put it into the finished parts bin. And when we analyze that strategy, we can see here that we've managed to eliminate that waiting time in the process. So now we've improved the efficiency of each of the individual assembly stations. We need to make sure that we can actually transport the finished products from each of the stations to the shipping department. And we've modeled the transporter here, the transport system. And the first strategy was to have the transporter stop at every single station, pick up the finished goods, and by the time this transporter gets to the last three stations, it's already full. And so we've got finished products kind of basically blocked at the last three stations. We can't get the finished product from those last three stations to the shipping department. Now we've got a couple options. We could either suggest that we go buy another transporter, which might be foolish, but we might be wasting money on purchasing an additional piece of equipment. Why not test some other ideas and see if we can't leverage the existing resources we have? And so we're running another simulation here, just looking at the transporter stopping at every other station and picking up the finished goods and then delivering them to the finished parts to shipping. And here we can see that we don't have any blockage any longer, and that we're able to deliver all of the materials to the points that they need to be in the plant. This ultimately improved the overall throughput of this factory, and we managed to do it without having to purchase any additional capital. And then lastly, And we often hear about discrepancies, big gaps between product design and production, and what actually happens in the shop floor compared to what the product designers actually intended. And as our products grow more complex, we're seeing that there's more errors and inefficiencies that are occurring in the production environment. And when that's the case, big benefits can be gained by bringing all of the engineering and manufacturing together into one place, into the digital twin, and give everybody in the organization a clear understanding of how the process is expected to perform and how it's actually performing. And manufacturing execution is where we close that loop between PLM and the manufacturing operations management. We've made a lot of great progress in merging the virtual and the physical worlds of manufacturing. And what we can do today is we can easily define digital process descriptions in the form of NC work packages or offline robot programs and even electronic work instructions, and deliver those to the point of execution to ensure that we've got the right tools and the materials and the operator instructions to be able to complete the particular task that they need to. And so by digitalizing the connection between design and production, we also obtain this ability to gain better insight into production performance, and we're able to feed process improvements as well as non-conformances in the process, as well as even quality issues back to the design department and the manufacturing planning departments. And you can only do this if we're taking advantage of a complete digitalized process all the way from design through manufacturing, planning, and onto production. If we do it properly, we can be ensured that the process is going to run as we intend it to, and if there's something different, we can use that intelligence or that change to help us understand whether or not it'll work with our digital twin, and then continuously improve. So to finish up, in our particular case, the digital twin helped Siemens achieve the objectives of being more flexible and more efficient. Siemens took a lot of the different recommendations that we discovered in the digital world and applied them to their real production process. And I think all of you can do it too. I think there's 3 steps that you can take to help you take a move into this direction. The first would be to digitalize your connection between your product bill of materials and your production plan. I think that you can take advantage of the digital twin and leverage our simulation capabilities to be able to validate that your process will work properly. And you can connect PLM to the physical world of manufacturing and close that loop. So with that, I'm finished, Paul. Hand it over to you.
Okay, thanks a lot, Aaron and Mike. Really appreciate it. It's a very exciting area. So hopefully from those 3 examples you have a better appreciation for the breadth of our portfolio, the integrated nature of our portfolio, and the fact that they're all running on the same backbone, that is Teamcenter. So just on behalf of all my friends and colleagues that were up on stage with me today, I'd like to thank you for your attention and wish you a good rest of the day. Thank you.